So in this video, I'm going to show you how to build half adders and full adders, and these make up the building blocks for computer arithmetic. So I'm going to do a quick review of binary addition. So in binary addition, we're adding two numbers, what are called the augend and the addend, together to produce the sum. And we do this by, in each bit position, the sum of the input bits in that position to produce a sum bit and a carryout that goes into the next column. So if we look at the first bit position, we have only two input bits because there's no carry into the first bit position, and we'll call these two inputs X and Y. And it doesn't really matter which is which because both these bits have the same weight. And we're going to use these two inputs to produce our two outputs, which are the sum bit, which is down here, and the carry bit, which is up here. And the thing that's important to understand is that the sum bit has the same weight as the two input bits, whereas the carry bit has 2 times the weight of the input bits and the sum bits. So let's go ahead and build the truth table for the circuit that will take the two input bits X and Y to produce the sum bits S and the carryout bit C. So there's 4 possible combinations of our input bits X and Y. And when we sum X and Y together, when 0 plus 0 we get 0, that means we can represent that with a 0 in the 1's place coming out of this bit position and a 0 in the 2's place. When we add 0 and 1 together, that's the value 1, so we need a 1 in the 1's place and a 0 in the 2's place. Similarly, 1 plus 0 is still equal to 1, but 1 plus 1 is equal to 2, so we need a 1 in the 2's position, the carry out, and a 0 in the sum to be the output of this circuit. So given this truth table, we can implement this with a relatively simple circuit. That if we look at the carry out is only 1 when X and Y are both 1. And so we can implement that with the expression XY or just an AND gate to produce the carry out signal. The sum is a little more complicated, but it's something that we've already seen also, which is an XOR gate. Recall that an XOR gate, XOR operation, is an odd detector. So when we have an odd number of 1s in our input, our outputs are going to be 1. So the sum is just the XOR of X and Y, which can also be written as X naught Y or X Y naught. And these two gates together implement our half adder. In the second bit position and every subsequent bit position, we're now going to have 3 input bits. And the reason why is because now we have a carry in bit, which was the carry out of the previous bit position. So we have 3 input bits. Again, they're all going to have the same weight. And we still have the sum bit coming out and the carry out, which still has twice the weight of the sum bit. So let's see how to produce the truth table for this circuit. Now we have 3 input bits, and I'm just going to sum them all up because they're all the same weight. So 0 plus 0 plus 0 is 0. Whenever there's only 1 bit set, the output's going to be 1. If I have 2 set bits, the output's going to be 2. And when all 3 bits are set, the output's going to be 3. So now I just need to figure out how to represent these values with our sum bit that is worth 1 and our carry out bit that's worth 2. So to represent 0, I set both carry out and sum to be 0. To represent 1, I'm going to set sum to 1 and carry out to 0. To represent 2's, I can set the carry out to 1 and the sum to 0. And to represent 3, I need to set both the carry out and the sum bit to 1. So the sum turns out to be, again, a relatively straightforward function. We see the sum bit is set when our sum is an odd number. So again, we're going to think XORs because XORs are odd detectors, and in fact, by XORing all of the input bits, we're able to get the circuit for the sum. So here's our expression for the sum, which is again just the XOR of X with Y and with Cin. The Cout expression is a little more complicated. Its Cout is 1 whenever X and Y are 1, or when Cin is 1 and exactly one of X or Y is 1. So either X is 1 and Y is 0 with Cin is 1, or Y is 1 and X is 0 when Cin is 1. So those are the 4 cases where Cout is 1. So this expression handles Cout. So it turns out this full adder circuit can be implemented with 2 half adders, which is sort of where they get their name. That the sum bit is the XOR of X, Y, and Cin. So by connecting these 2 half adders here, we have X XOR Y, and we bring Cin in, so this is X XOR Y XORed with Cin. And then down on this path, we have X and Y. And what we're going to do is we're going to take X XOR Y and that with Cin. So here we have X XOR Y. That ended with Cin, which is this part of the expression. And then we're going to OR that with XY to get the whole expression. So we can build this full adder just by taking 2 of the half adders that we've already built and connecting them as is shown here. So we'll take the S output of the first adder and connect it to one of the inputs of the second half adder, and we'll take the C output of the first adder along with the C output of the second adder, and that will be the Cout, and the S output of the second half adder will be the S output of the full adder. And we'll need 1 additional OR gate. And that's how you build a full adder.